Here's problem 211. A toy rocket launched from the ground rises vertically with an acceleration of 20 meters per second squared for 6 seconds until its motor stops. Disregarding any air resistance, what maximum height above the ground will the rocket achieve? Well, we actually are going to have two parts to this problem, so this is actually a bonus problem. Yay! So what we're going to do is treat it as two kinematic problems and combine the two results. First of all, we're going to shoot a rocket from the ground, initial velocity of 0, and then we're going to have, this will be the first part, and in this part the acceleration will be 20 meters per second squared because that's what we're given. So even though there's gravity acting on it, all things considered, it still manages to accelerate at the value of 20 meters per second squared for 6 seconds. Then we have the second part of this journey where it finally goes up to its maximum height. The motor has been shut off, so on the second part the acceleration is the acceleration of gravity, which is down towards the center of the earth. And if we were thinking that our velocity is going up, and that's our positive direction, this acceleration will be a negative 9.8 meters per second squared because it's in the opposite direction. We want to find the displacements for these two sections, these two kinematic problems. And we can only deal with the kinematics of each of them separately because that's when we have constant acceleration, and kinematics only applies to constant acceleration. Alright, so if we look at the first segment, the first part, we have an initial velocity of 0 because we launched it from the ground. We have an acceleration given as 20 meters per second squared. And what else do we know? It goes for 6 seconds. It's called T1. And we want to find delta y1, and let's find our final velocity as well. So we know that displacement delta y1 should equal our initial velocity times time plus 1/2 acceleration times time squared. Initial velocity being, in this case, 0 because it started from rest. So we have this is equal to 1/2 times 20 times 6 seconds squared. That would be 10 times 36, or 360 meters. That will be our delta y1. Our final velocity will equal our initial velocity plus acceleration times time, and in this case our initial velocity was 0. So this is just going to be 20 times 6 seconds is 120 meters per second. So that'll be our final velocity for this first leg. Well, that final velocity for the first part, first leg, will be the initial velocity for the second part. So if we look at our second part, our initial velocity in this part is actually going to be 120 meters per second. The motor is shut off, so the only acceleration is that due to gravity. So our acceleration is going to be a negative 9.8 meters per second squared. We don't know the time to the top, but we do know that our final velocity on the second leg will be 0 because we're going to go as high as we can go and go no further, and when we do that we momentarily will stop at the top. And the two things we don't know is the time and the displacement delta y2. We don't need to know the time, but we do need to know this delta y2. So if I focus in on the three variables that we do know and the fourth one that we're asked for, then we can set up our equation based on that. And it looks like I'm going to use kinematic equation number 3. So final velocity squared equals initial velocity squared plus 2 times acceleration delta y2 in this case. Our final velocity for the second leg is 0 because we came to rest. So we'll solve this for delta y2. delta y2 will equal a negative v naught squared over 2 times acceleration. This would be a negative 120 meters per second squared over 2 times a negative 9.8. And what is that? (734.7 meters). So in the first leg of this journey, first part, we went 360 meters. In the second part, we went 734.7 meters. Our total height that we achieve will be equal to our displacement delta y1 plus our displacement delta y2, the combination of these two displacements. So we have 360 plus 734.7 gives us 1,094.7 meters. So the maximum height above the ground that this rocket achieves is 1,094.7 meters above the ground. So the way to do these kinds of problems is to break them up into separate kinematic problems. In this case, we had to use the final velocity of the first part to be our initial velocity of the second part. That was our connecting information. But once we did that, the rest of it was just kinematic equations for each zone of constant acceleration.